Good afternoon, everyone. Thank you for a nice introduction. I am Roshan Mangal from Jeju National University, a PhD candidate working under the supervision of Professor Youngsun Mok. And today I would like to present on a topic that you can read here. Before beginning my presentation, I would like to I feel obligated to give the disclaimer that I personally feel this work is not even remotely related with quantum, but that could be because I am not expert in the field, and I hope the greatest mind of this era who are present in the hall can correlate and give some constructive comments on my work. So to start my presentation, this will be the content of my presentation, and to briefly talk about the motivation behind the work, the energy storage, and we all know that battery and supercapacitor and such kind of energy storage equipments are necessary for various kind of applications. And among those things also, the wearable, the flexible power sources can be used for wearable and conforming electronics for sensing, healthcare, and next generation smart appliances. So for flexible power source, I chose the carbon cloth mainly because of its flexibility, obviously, and the lightweight, strength, cost effectiveness, and the environmental friendly nature, among many other benefits. And however, the conventional active material growing on the carbon cloth surface has some inherent disadvantages, such as delamination of the active material from the current collector surface, and also the active material evolution to less electroactive phases and morphology degradation upon many cyclic charge discharge. Because of that, we propose the novel approach where we embed the active material, the electrocatalyst, inside the carbon fabric to improve the stability and also the electrochemical properties. So for that, first we actually this work is divided in two parts. First, I would like to talk about supercapacitor, then lithium-ion battery. Then I will combine those two works. First, we worked on supercapacitor, where we grow some metal on the carbon cloth layer. Then we grow another layer of metal organic framework on that layer. Then we did embedding of the electrocatalyst inside the carbon fabric. Then we did the oxygen functionalization. This oxygen functionalization step seems later we found it has greater implications in the energy storage work. And finally, we did the sulfurization to improve the electrochemical storage ability, such as improving the capacity of the supercapacitor. So later we did the several physical chemical characterizations. Among them, here I show the XPS analysis, and in this XPS analysis we see that after the oxygen functionalization step, we did the sulfurization. The oxygen functionalized and sulfurized sample shows the stoichiometric sulfurization rather than without oxygen functionalizing the metal. So that means oxygen functionalization helps better sulfurization. And after that, we did some supercapacitor study. Here we can see the generic cyclic voltammetry and galvanostatic charge discharge curves. And we can see that the oxygen functionalized and sulfurized sample shows the best result among all fonts. And finally, the last figure, figure I, shows the optimization of the oxygen functionalized and sulfurized sample, and the 400-degree oxygen functionalized then sulfurized sample shows the best specific capacity. So we chose that one for further study. And then we did the we fabricated the asymmetric supercapacitor device using that optimized cathode and cherry flower biomass derived activated carbon anode. And here also you can see the cyclic voltammetry and galvanostatic charge discharge plots, and finally the capacity plot of the asymmetric supercapacitor device. So the capacity is quite good when you compare with the previous literatures where they use the similar kind of active materials. And these are further results where we see the asymmetric supercapacitor device performance. The most interesting performance here is the figure E, where we see the stability of around 45,000 cycles for a supercapacitor device. That is quite good result if we compare with the previously reported results, where we mostly see around 10,000 to at most 20,000 cycles. So we believe this exceptional stability comes from the embedding of the electrocatalyst inside the carbon cloth. So and we did some practical applications of that supercapacitor device. And after supercapacitor, I would like to talk about some battery work. This is completely different active material that was nickel cobalt, and it is cobalt molybdenum. Here we use the muscle inspired polydopamine coating, hence the title of my presentation, the nature inspired. The polydopamine coating over the metal oxide or metal sulfide nanoparticles is believed to give the higher stability in particularly the battery work. So we use that, and we did the FSM analysis in last G, H, and I figure. We can see the translucent carbon coating. Actually, we did the polydopamine coating, then we did the carbonization of that one. So we get the nitrogen doped carbon coating over the metal sulfide nanoparticles. And we did further the XRD and HAD of TAME analysis, and particularly in figure E, we can see the metal sulfide core and the nitrogen doped carbon shell. So we confirm the nitrogen doped carbon coating is very nicely formed all over the metal sulfide core. And finally, we did the battery electrochemical characterizations. And here we can, if we compare figure B and figure E, we can see the capacity of carbon coated battery has quite high compared to the non-coated one. And also the figure G, the stability of the carbon coated electrode has surpassed the non-coated one with almost like 600 around 400 cycles. It reached around 600 total cycles, whereas the normal carbon non-coated electrocatalyst was showing only around 200 cycles. And the nitrogen doped carbon coating is helping on the adsorption desorption charge storage, as well as the conventional intercalation is happening inside the core, that is metal sulfide. So from those two work, we hypothesize that doing the oxygen functionalization thing and embedding the catalyst inside the carbon cloth, then doing the carbon coating should give very good performance when you implement in battery. And doing so, we can eliminate the use of binders such as the PBDF or CMC, those things, because binder is a dead mass that does not contribute in charge storage. And if we can just embed material inside and do the carbon coating, it will give the highly stable electrode material. So we hypothesize those things, and so first few figures are from the earlier, and the last one is we did the polydopamine coating on the carbon cloth after embedding, oxygen functionalizing, and sulfurizing the active material. So after doing that, we can see the FSM image. Figure A, B, and C is the nickel layer. D, E, and F is the ZIF67 MOF, and G, H, and I are the embedding of those two things inside the carbon cloth. This looks rather pleasing, like strawberry. I like to call it the strawberry shield-like structure. And figure J, K, and L is the after sulfurization, and figure M to O shows the carbon layer depositing over that catalyst. So we can see in figure O that the translucent kind of coating is present. That is the nitrogen doped carbon derived from the polydopamine. And also this figure, these are the nanoparticles embedded inside carbon fabric, which were not sulfurized. And here also we can see the translucent kind of coating, that is nitrogen doped carbon. So this is EDS image of the same samples, and here also we can see the presence of the wanted elements. Particularly figure A and B, we can see if we see the sulfur element, the sulfur is present in the kind of island structure in figure A, that is oxygen functionalized and sulfurized sample, whereas sulfur is present all over the places in the figure B. That is mostly because of the after oxygen functionalization, the stoichiometric sulfurization is happening in the catalyst surface, but in figure B, the sulfur is depositing as an elemental sulfur rather than the stoichiometric metal sulfide. So that is the point to be noted. And finally, we did some electrochemical characterization, fabricating a Cr203 coin cell with that electrode. And here we can see that the capacity is surprisingly high, and the stability is also good after the carbon coating. Figure A and B is of the same electrode that was carbon coated and oxygen functionalized sulfurized electrode, and whereas figure C was sulfurized but not oxygen functionalized and carbon coated one. So not oxygen functionalizing cost us around almost 1500 milliampere hour per gram of capacity, whereas after oxygen functionalization, then sulfurization, and then doing the carbon coating gave us the best performance, quite surprisingly high capacity. And figure D is particularly the interesting here. The carbon coated electrode shows good performance until the 100 cycles, whereas the non-carbon coated one it starts to damage around, not damage, but it starts to fade around 20 cycles. So the carbon coating is definitely working here, and also the oxygen functionalization has great importance, as we see. And but interesting thing I want to point out here is the I think the theoretical capacity of the active material I am using is around 800 milliampere hour per gram, but here we are seeing around 2500 milliampere hour per gram. So some chemistry is going on there that needs further study. And yeah, anyway, the result is promising, and we are working on further improving the performance. And so with this slide, I would like to conclude my presentation. The surface grown electrocatalyst has moderate capacity and poor stability, whereas the embedded electrocatalyst has moderate capacity but good stability, and the embedded functionalized and the carbon coated electrocatalyst has excellent capacity as well as the excellent stability. So with this slide, I would like to finish my presentation. Thank you for listening.
All right, any questions for the speaker? Yes.
Hi, thank you for the talk. So just on the previous slide, you had the two graphs showing, I think it was two different devices over a number of cycles. Though I noticed the number of cycles was fairly similar. I think it was 100 and 120. Does the improved device last much longer before it begins to degrade, or do they last a similar amount of time?
Actually, thank you for your question. It's a nice question. It's still running. The 100 cycle one is around 105 cycles, so yes. I rounded it up to 100 cycles only. The 120 cycle cell is already going down, so I need to see how the optimized electrode performs. It's still running actually.
Okay, cool. Thank you.
If I may ask a question, so if you go back one or two, oh, sorry, the presentation. Can we put the presentation back? Okay. If you go back a few slides, there was I think you have the, was the voltage versus capacity.
Yes.
And the first cycle looks very, very different from the last cycle.
Yes.
So, yeah, I wonder why was that? Yeah,
for example, this one.
Maybe go back, yeah.
This
so
one.
If you look at panel A, right? The first behavior of the first cycle is very, very different from the
yes.
last cycle. So
yeah.
what is the, and then your capacity stays about the same. So what's the, how can you explain that?
So yeah, thank you for your question. The first cycle is the lithiation. The downward is lithiation, and in the first cycle there is many chemistries are going inside there, like formation of solid electrolyte interface. So we lose some lithium there. There is some construction and reconstruction of chemical bonds, and it is mainly because of the formation of solid electrolyte interface. The chemistry is little different, but after second cycle the chemistry is stable. Only the same bonds will be forming and deforming. There will be no too much formation of solid electrolyte interface, the dead mass. So the cyclic pattern is similar after second cycle, but in the first cycle the chemistry is slightly different, so that's why the pattern is little different.
Interesting. Now, how soon are we going to see these in the, in the store?
In the market?
Yeah, in the market.
Well, I would love to see them as much as you, but we are hoping in few years. Let's see. It's in the lab scale only now. Actually, I have already prepared the full cell as well. It is working nice, but to commercialize it, we need to do further works.
Fabulous. Thank you very much for the talk.
Thank you.
Appreciate it.